Parameter estimation. The mean vector mu is defined such that each of its elements is the mean of one column of x. That is, the expectations of x is equals to mu, which is equals to mu1, mu2, mu3 until mu d to the transpose. The variance of xi is denoted as sigma I squared, and the covariance of two variables xi and xj is defined as sigma ij, which is defined as covariance of xi xj, which is by definition equals to the expectations of xi minus mu I times xj minus mu j, which is equals to the expectations of xi xj then minus mu I mu j, with sigma ij equals to sigma ji, and when I is equals to j, sigma ii is equals to sigma I squared. With the d variables, there are d variances and d times d minus 1 divided by 2 covariances, which are generally represented as a d by d matrix, named the covariance matrix, denoted as sigma, whose ijth element is sigma ij. That is, sigma equals to sigma 1 squared, sigma 1, 2, and so on until sigma 1d, sigma 2, 1, sigma 2 squared, and so on until sigma 2d, sigma d1, sigma d2, and so on until sigma d squared. Diagonal terms are the variances, the off-diagonal terms are the covariances, and the matrix is symmetric. In a vector matrix notation, summations is defined as the covariance of x. Sigma is defined as the covariance of x, which is equals to the expectations of x minus mu times the transpose of x minus mu, which is equals to the expectations of x times x transpose, then minus mu times mu transpose. If two variables are related in a linear way, then the covariance will be positive or negative depending on whether the relationship has a positive or negative slope. But the size of the relationship is difficult to interpret because it depends on the units in which the two variances are measured. The correlation between variables xi and xj is a statistic normalized between -1 and +1, defined as correlations of core of xi xj, which is equals to rho ij, by definition is sigma ij divided by sigma I times sigma j. If two variables are independent, then their covariance and hence their correlation is 0. However, the converse is not true. The variables may be dependent in a nonlinear way, and their correlation may be 0. Given a multivariate sample, estimates for these parameters can be calculated. The maximum likelihood estimate for the mean is the sample mean, m. Its ith dimension is the average of the ith column of x. That is, m equals to the summations of x to the t, summing for index t starting from 1 to n, then divided by n, and with mi equals to the summations of xi to the t, summing with index t starting from 1 to n, then divided by n, where I is the index equals to 1 to 3 until d. The estimator of sigma is as the sample covariance matrix with entries si squared equals to the summations of xi to the t minus mi to the square, summing with index t starting from 1 to n, then divided by n. Sij, the sample covariance between two different elements, is defined as the summations of xi to the t minus mi times xj to the t minus mj, then summing for index t starting from 1 to n, then divided by n. These are biased estimates, but if in an application the estimates vary significantly depending on whether we divide it by n or n-1, we are in serious trouble anyway. The sample correlation coefficients are Rij equals to Sij divided by Si times Sj, and the sample correlation matrix R contains Rij.